There's the Earth's magnetic field. You saw the video about it, right? What does the Earth's magnetic field do for us? Protects us from solar radiation. And what are the northern lights that we see from time to time? Yeah, and why do we see it in the north? Well, because that's where the field strength is strongest, right? And that's where it's sort of taking all those charged particles, and if they're not being deflected, then they end up going towards the Earth's pole.
Would it be magnetic strength that helps with keeping the Earth on its axis, I guess, rotating around the sun?
No, I don't think so. No. Yeah, I don't think there's any relationship there.
What's going to happen with the satellites? That's true.
Yeah, I don't know. Okay, so let's back up a little bit. Is this the first thing you have? I think so, right? Yeah? Okay, good. We've seen that magnets can exert a force on objects that touch them. I haven't shown you that yet, but certainly you've seen that already. For this reason, we speak of a magnetic field. It's that field concept again, around a magnet in the same way that we speak of an electric field around a charged object. So here I have a clip art magnet and two PowerPoint little things that are supposed to represent like metallic chips. And they are being attracted to the magnet. How come? Because they are in the magnetic field. Now this horseshoe magnet here would have a north and a south, right? And remember, north to south like this, and that field would extend out. Now, if these are neutral, non-magnetic, would they be more attracted to the south, more attracted to the north? Is north stronger than south? No? Equally attracted? So these little chips would probably just then be attracted to whichever pole was closest, exactly. Okay? Why do they have horseshoe magnets? Like, what's the point? Like, why bend it into that horseshoe shape, do you think? They do look cool. Well, they're handy to handle, right? But stop and think about it. I'll get out a couple here while you're thinking about it. We can have one. Like, what's the advantage? What's the advantage to one like this compared to one like this? Come on, think, you guys. You can what? No, I mean, like, actually, like, at home or in the shop or whatever.
You hang them up.
You get more power.
Do what?
You get more power.
You get more power. How come? Okay, and so that makes the field lines what? Closer together, right? Here, you just got one pole. You're trying to pick something up. You just got one pole. But here, you got two. You're basically doubling the power because, like, neutral objects, they're attracted to, right? They don't care. It's not like positive and negative kind of thing, right? So, like, if I've got, like, paper clips or something like that, theoretically, this one should be stronger, right? Woo! That was pretty boring.
That was disappointing.
Oh, disappointing. How can I test the strength of these?
Science. By pulling on the paper clip.
Would that work? You could, but could you say which one's stronger here, based on this?
Well, you got more of it covering the other one.
That's true. That's true. I don't know. Would these be equal magnetic strength? Could be, but tough to tell, right? How would we determine, how would we define, how would we come up with a measure of stating which magnet is stronger? Like, what would be the determining factor? Do you think? Well, he's sort of have, he's on the right track there with further comment.
That's not a bigger object thing?
Okay?
That's not
No, I mean, like, definition-wise. Like, how would we write a formal definition for what would determine the strength of a magnetic field? Well, it's got to do with the lines, right? And Willie said, he just didn't realize that he was right. Because the poles are close together, that brings those field lines together closer, right? And we know that the closer the field lines are, the stronger they are. So we could come up with a way of saying how many field lines there were in a certain region, and that would be kind of a way of measuring the magnetic field strength, or defining it, which is where we're going to get to right away. A magnetic field is represented by drawing in magnetic lines of flux. That's what those are called. These are lines drawn so that a tangent at any point will show the direction of the magnetic field. So, in other words, if that's my magnetic field right there, the tangent would be right there. So the magnetic field at that point is that way. The direction of a line of flux is from North Pole to South Pole. North to south, but that is on the outside of a magnet, and from south to north on the inside, and you can see the red lines there. Do you guys have a picture that you can?
Yep.
You do, eh? Okay. Oh, and I threw them on for you. Holy moly. I'm lazy.
Can we play with superconductors?
No. Now, I'm going to show you the iron filings in a bit. One line of flux can cause many lines of iron filings. When you actually sprinkle out the iron filings, they're not necessarily one for every line of flux. Okay. So this dude here, Wilhelm Eduard Weber, he gets the honor of having the unit of a magnetic line of flux is called 1 Weber. If there's 2, it's 2 Webers, and so on. And the symbol for that is WB.
Wilhelm, as in Wilhelm scream? Yes.
Sure.
What do you do?
Not shave.
And apparently also scream.
But like, why is it aimed at?
Why is it aimed at him? I think he's like one of the heavyweights in the magnetic field history chart. I don't really know, actually. I don't know a whole lot about him.
That's why he screamed. He got punched.
Weber. The entire group of lines of flux is called the magnetic flux, and it has a really weird symbol. It's the Greek letter phi. So it's a circle with a line through it. Okay? The entire region is called the phi, the flux, and every one is a magnetic line of flux, and each one is referred to as how many Webers. It's kind of confusing, I know. It's not my favorite thing to explain. Okay, so the magnetic field strength. A electric field exerts a straight, attractive, or repulsive force upon a charged object. That's an electric field. A magnetic field will exert a particular force upon a charged moving object. If you have something, an electron that's moving, a magnetic field will exert a force on it, and this force is perpendicular to the motion of the charge. And it's also proportional to the velocity of the moving charge. So what that means is if you've got a wire in a magnetic field, there will be a force on it. And that, my friends, is the basis behind, anyone know? The electric motor. An electric motor is simply, you've got your electricity running through this wire here, and it's inside a magnetic field, and there's an actual force on it. It pushes it up. And if you configure it properly, you can force it up and then rotate it, and that's what an electric motor is. Okay, whether it's in a car, like a toy car, golf cart, electric lawnmower, whatever. That's the idea behind it. Okay? We may or may not get a little bit farther into that in a bit. So there are 2 methods of defining magnetic field strength. I've sort of alluded to one already. One is in terms of the amount of force exerted per unit of moving charge. That's the complicated one, that wire stuff that I was just talking about. And the second one is, which is a little closer to understand, or a little easier to understand, use the idea that magnetic field strength is directly related to the concentration of flux lines. In other words, how close the lines are together. How close the lines are together. And we're going to call this lines of flux per unit of area. And I'm going to give you a formula right away.
There's on there.
Is it right there? It's right there. Okay. You guys got like nothing to write here, nothing to do. Very disappointing on my part. Magnetic field strength is the number of lines or area, or B equals phi over A. A weird looking kind of completely unrelated formula from all the ones we've sort of seen already. It's on its own. B equals phi over A. And B is measured in Tesla. Here's some more crazy words. B is magnetic field strength, measured in Tesla, named after Nikolai Tesla. I can tell you about him when he... Tesla and Thomas Edison were like... No, they were arch enemies. In a sense, they fought, not in a literal fistfight sense, but they fought with words. Edison definitely won.
Unless you're looking at what type of power they use.
Yeah.
In that case, Edison won't hurt. Tesla.
Edison is the more well-known. He went on to invent and discover and promote many items. Tesla was more of a scientist. Edison was a bit more of an entrepreneur kind of thing. There's actually a huge sort of worldwide underground cult trying to promote Tesla kind of thing. There's a workshop in where Tesla worked, I think it's in New Jersey. It was going to be like torn down and put up like a 7-Eleven or something other. And all these nerds got together and bought it, and now they're going to like restore it. Pardon me? No, I don't think it's anything like that. The car company Tesla is named after him. Tesla was, pardon me? Yeah, those are the guys that came up with those super batteries like about a month ago. Charge your hubs, yeah. Nikolai Tesla. He was bad, like in the good sense. So B is measured in Tesla, phi is measured in Webers, those are the units, and A is measured in square meters. Okay? Now, what do you think this all is down here? I'm just making the analogy. If you've got the formula F equals MA, so F equals MA is like B equals phi over A. It's the formula. What are the units for F? Newtons. What are the units for mass? Kilograms. What are the units for acceleration? Meters per second squared. Okay. What are the units for magnetic field strength? Teslas. Phi is Webers. Area is square meters. So T is equal to WB over meters. Those are the units, or square meters. It's pretty easy when you get a hang of it. Let's have a look at one. Do you have this answer?
Yeah.
You don't have the answer? So you have to actually do something?
Yeah.
Well, that's good. Okay.
There's a couple of fill in the blanks.
Well, that's good. In a 25 square meter area on the Earth, there are 1.25 times 10 to the minus 5 lines of flux measured. What is the field strength of the Earth's magnetic field? I'm going to tell you. We're going to go, we're looking, what is the field strength? We're solving for B. So we're going to write B equals phi over A. Do you need to write that?
Yeah.
You do, excellent. B equals phi over A. Do I know the B?
No.
I do not. Do I know the phi?
Yeah.
It is
1.25.
1.25 times 10 to the minus 3. So I'm going to write B Earth because it's the magnetic field strength of the Earth. 1.25 times 10 to the minus 3 divided by 25 square meters. How big would 25 square meters be? 5 by 5. I'd say about a quarter of this room. A quarter of this room. So divide that out, and what do you get? 5.0 times 10 to the minus 5 pascals. This is it says a constant value. I would call it a relatively constant value. The video that we watched the last couple of days has shown us that the Earth's magnetic field is decreasing. It's stronger near the poles, weaker near the equator, so it's sort of an overall average. That doesn't sound very big, eh? 5.0 times 10 to the minus 5. It's a small number.
Yeah.
But yet it will move a compass.
And we are like, how many kilometers in the core?
That's true. Would it be stronger at the Earth's core?
Wait. I feel like it's a little bit.
Maybe. I'm not convinced of that, though.
How wide is the Earth?
How wide is the Earth? The radius of the Earth is 6,400 kilometers. Why do I know all these things?
No, it's like 13,000 kilometers across the world.
Yeah. Like if you walked up to the average person on the street and said, "What's the radius of the Earth?" What are the chances?
6,400.
It's disappointing.
So now I don't.
Now you know, Grant.
That's a lot of polygons.
That is. Okay, do you want to stand up and come get one?
I feel like I could stick right
Yeah?
Yeah.
Why don't you pass out the rest, yeah? You'll do better if you get up, right? Okay. You guys give those a whirl. Let me explain how some of these conversions work, you guys, okay? Because this is kind of important too. Converting from in metric system is easy. You just gotta stop and think about it, okay? So in 1 meter, that would be equivalent to 100 centimeters, right? So 1 meter by 1 meter, that is 1 square meter, which is 100 centimeters by 100 centimeters, which is 10,000 square centimeters. Which means that question that has 50 square centimeters, you have to divide by 100 squared to get to square meters. Divide by 100, divide by 100, so you get 0.0050.
Divided by 1,000.
10,000. 10,000. Move the guys to place four spots, yeah. That's sort of a side byproduct,
Too bad I have a question.
learning that, yeah.
It says the small.
Yeah?